Number Systems Module 1. The contents for this week material can be found on Canvas. I'm providing the PDF for chapter number 1 from this book, Digital Electronics: A Practical Approach. You do not need to buy this book. I'm providing everything on Canvas so you can study for this material. By the end of the week, these are going to be the learning objectives, and the videos are going to focus on binary numbers and converting between bases. For Intro to Mechatronics Systems 2, we deal with the brain of the system, so we are dealing with computers. Inside of those computers we have ICs, which are these modules here that you see over here, and inside of an IC we have digital logic, and these ICs exchange information by using binary numbers. And why binary numbers and not another type of coding? We live in a digital world, and information can take the form of voice messages, piece of music, photographs or video, and we need to find a process to encode that information. We need to find an appropriate code to represent this information. Let's start with an obvious one, which is the alphabet. We have 96 elements, we have 26 lowercase characters, 26 uppercase characters, 10 numbers, and 34 special characters. We normally use these to exchange information between humans, either by writing books or letters, but how good is this code to represent information in a digital world? Can we use a more powerful coding mechanism rather than these 96 elements? What about Mandarin, profile of Chinese, where you can have as many as 40,000 characters to represent information? Well, there are pros and cons on these approaches. One of the advantages of using the 96 characters is because it's simple to distinguish the characters between each other, while that is a disadvantage by using the Mandarin. On the other hand, I can encode a lot of information in just one symbol on the Mandarin code, rather than fewer numbers convey less information on the English one. Bottom line, do I want a code with less characters, less symbols, or do I want a code that conveys a lot of information on each symbol? To answer this question, we need to set one more requirement. We are dealing with computers, electronics, so we want something that is inexpensive and reliable, and something that is tolerant to errors. When we set this requirement and we go back to these two coding mechanisms, are these encoding mechanisms robust and tolerant to errors? Well, let's see, for example, for the English alphabet here. What if I have an A, and let's say that I transmit an A and I get an error which is putting a dash like this on top of an A. It's still an A. It's a little bit tolerant to errors. What if I have a V and I put another one? Same thing. But what if I have a C and now I have something like this? Well, now it starts becoming similar to a G. What if I have an F and I get an error like this? Now it looks like an E. Same thing applies for Mandarin. Look how just a simple dash on the symbol, as you can see it over here, can alter the meaning of the information that you are encoding. Can you find a better one than the English and Mandarin? What about if I use 0 or 1? Two symbols. The fewer the symbols the code has, the easier it is to distinguish the symbols from each other, and the more robust the code will be. And this will satisfy the requirement that we set up initially. That's why we use binary numbers, and we have binary code, so 0 or 1, sometimes also known as true or false, and these we call these bits, and we call this base 2 number system. And how much information can we convey with just one binary symbol? Not a lot, right? Well, But that's the same thing with just one letter of your English alphabet. When you start connecting letters together to form words, this is when you start storing more information. And the same happens when you start putting more bits together. If I have just 0 or 1, it's 1 bit. If I put 2 together, I get 2 bits. If I put 2 bits together, I get 4 bits, which is a nibble. 2 nibbles, it's a byte. 2 bytes, it's a word. And 4 bytes is a long word. How much information or patterns can be represented with binary code? The answer relies on using the powers of 2, and we're going to use this table a lot, where at your left you have the number of symbols, and if you do 2 to the power of the number of symbols, you get how many patterns or combinations you can have. This is what we're going to use for this base 2 number system, but let me cover a common problem that I find in classes when we are learning these powers of 2 for the first time, which is the difference between symbols and combinations. And then how can we use these also for binary numbers? So let's forget zeros and ones for now, and let's say that I have the dot symbol and the dot with a dash. So I have these 2 symbols. So if I go to my table with 2 symbols, I'm going to get 4 combinations. So if I go here, I have option 1, option 2, option 3, and option 4, or combination 4. So option 1 is going to be no symbols. Option 2 can be just the dot. Option 3, dot and the dash. And option 4 can be dot and the dash. So notice that those are going to be the 4 combinations that you have available. 1, 2, 3, 4. So the first one, no symbols. Second one, a dot and a dash, and then a dot with the dot and the dash. So now let's go over the same concept, but I'm going to use zeros and ones. So instead of my symbol being a dot and a dot dash, I'm going to use a 0 or a 1. So notice that I'm not combining the bits, I'm just saying that my symbols is either a 0 or a 1. Option 1 is no number, option 2 0, option 1, option 3 1, option 4 0 or 1. Alright, so if I go back to over here, this is what I will populate here. So option, let me do that. So let me erase these options over here, and if I populate with that, I get the first one nothing, second one 0, third one, and 0 and 1. But this is actually this is correct, but when we are doing binary numbers, this is not the way that we are using this power of 2. We're using these when we combine bits together. So what we're doing is, let me erase this part over here. So I will erase this. And now what I have is, I have 2 bits. So bit 1 and bit 0. All right. And with this bit 1 and bit 2, bit 1 and bit 0, these are my symbols, which is these 2 symbols. I can have 4 combinations. These bits can only have 2 possible values, either a 1 or a 0. So if I go here and if both are 0, this is going to be my option 1. If this is 0 and 1, this is my option 2. 1 and 0, option 3, 1, 1, option 4. These are my symbols, bit 0 and bit 1. This is what's go over here. And I can get 4 patterns or 4 combinations, which are these 4 patterns of combinations. On our next video we'll go over the 4 common number systems.